Okay, welcome everyone. I'm Sarita Adve. I lead the ILLIXR project with many students. We're really sad that due to various travel issues, most of us couldn't make it in person. We were really looking forward to this, but we have worked hard to give you all a good time. So welcome, and I will turn it over to Chinjun. But I guess before I do that, I should say that Jeffrey Liu, who's there in person, he's a key member of the ILLIXR team, and he will help coordinate the online. And if you have questions, just ask away anytime. Please interrupt. This is meant to be a discussion. And Jeffrey will ensure that we all hear if the microphones aren't good enough. Okay, thank you so much. So Chinjun, please take it away.
Yeah, thank you, Sarita. Hi, everyone. My name is Chinjun Jiang, and thanks for joining us on the ILLIXR tutorial today. So I will be presenting about ILLIXR and some of our work with my colleagues Stephen, Jeffrey, Ihan, Rahul, Vignesh, Boyan. And ILLIXR is also contributed by many collaborators, which we will acknowledge later on the slides. Okay, today's agenda is as listed here. We will first give a broad introduction on immersive computing and the grand challenges and opportunities it gives us. Next, we will give an overview of XR and ILLIXR. We will also give you a hands-on demo of how to set up and run ILLIXR and a walkthrough into the important features in ILLIXR. So after that, we will take a deep dive into our research on distributed XR and how ILLIXR can be utilized for more research on distributed XR. Finally, we will briefly cover other research happening around ILLIXR and how you can contribute to ILLIXR or use ILLIXR for your own research. There will be a question time at the end, but as Sarita said, please feel free to ask any questions in the middle. All right. So immersive computing is broadly referring to the seamless integration of the virtual world with the physical world. It has many forms, including but not limited to virtual, augmented, and mixed reality, which together called extended reality or XR. So immersive computing has been widely adopted in many areas, such as healthcare, education, science, industry design, and so on. And there's no doubt that immersive computing has a potential to transform most industries and human activities. However, realizing this potential requires resolving the challenge of having XR devices that are comfortable, mobile, and can provide rich immersive experience for all day long. Unfortunately, we are still far from this ideal world. For example, the XR devices that we have today is usually the humongous and heavy headset, which can be of hundreds of grams. But ideally, what we want is something like our glasses, which is very light and comfortable. We also want the device to be of low power, such as hundreds of milliwatts, so it won't heat up our face. And the battery would ideally sustain for an entire day rather than just 2 hours with the battery pack in your pocket. And the resolution of the display is a number of users that can be supported in a distributed setting, and the richness of the 2D 3D models are currently not good enough for a perfect immersive experience. And finally, all these immense computations have to happen within a very stringent motion to photon latency, which is only 20 milliseconds for VR and 5 for AR. This introduces more design difficulties. So as we can see, there's no silver bullet for tackling this technology challenge for immersive computing. And instead, we need an end-to-end approach to integrate expertise from various domains. Unfortunately, there used to be lacking an open reference system or benchmark that would allow end-to-end and interdisciplinary XR research to be conducted. To help with this, we built ILLIXR, which is an open source end-to-end XR system to democratize full stack XR research. So now let's take a look at what ILLIXR is. So ILLIXR stands for Illinois Extended Reality Testbed. It incorporates many state-of-the-art XR components with a flexible and modular runtime, orchestrating the data dependencies and communications. ILLIXR is OpenXR compatible, and it can support many different applications developed with game engines such as Godot, Unreal, and Unity. And ILLIXR has been widely used by research teams in both academia and industry, which we will cover some of the examples today. So before we jump into details of ILLIXR, I want to first acknowledge the many students that have been contributed to ILLIXR over the past few years. I'd also want to thank our collaborators and advisors for their assistance and guidance along the way. All right, let's first see a few demos of ILLIXR running. So here you can see the user is wearing a Valve Index headset with a Z Mini camera attached to the front. And the entire system, ILLIXR system, is running on the desktop, and it takes care of everything from processing the sensor, to head tracking, rendering, reprojection, and finally projects all the pixels to the display so the user could see it. And this is the frames that the user actually sees through the headset. Here's another demo of a different application, which is called Flight Simulator, where the user can actually control an airplane with the keyboard or some controller. So the point is, I want to show you like ILLIXR is working very smoothly and provides a very pleasant experience. Here's another demo showing the development interface of ILLIXR. So in the middle, you can see a stereo camera frame showing what the camera captures about the user's surroundings. And on the left and on the right, you can see the third-person view and first-person view of what the user actually sees through the headset. Now on the bottom left, you can see a debug window, which shows all kinds of useful information that you can use to learn about the performance and characterize your system. All right, next, let's take a more close look into ILLIXR's architecture. So this is a higher level diagram of the entire XR stack, all the way from the applications to the hardware where the system is running on. So on the top, you can see XR applications, and this could be either applications written by yourself in languages like Vulkan or OpenGL, or it can be developed by some game engines such as Godot and Unreal. And then there's an interface that ensures the application could communicate with the runtime. And in our case, we use the OpenXR interface, and we use the open source implementation of OpenXR, Monardo. So in the middle, you can see ILLIXR, which is a combination of a communication interface, a runtime, and a collection of components. Right, and these components can be divided into 3 pipelines. The first one is the perception pipeline, which is responsible for understanding the user's positions and orientation in the physical world, and also the user's surroundings through many sensor inputs. Then there is the visual pipeline, which takes the generated information from the perception pipeline, such as the head pose, hand pose, eye pose, and the 3D representation of the thing, to actually generate the final pixels that the user would see on the display. And also, there's also a audio pipeline, which handles the audio encoding process and also the 3D spatial audio playback. We are actively adding new components such as scene understanding into ILLIXR to further improve the immersiveness of the experience. We are also exploring offloading some of the heavy computations of the device, for better power efficiency on device, which we will talk about more on this later. Okay, so next I will go over each of these components and give you a high-level overview of what they are and what they can do. So if you're interested in any of specific aspects, you can, the direction to go. All right, so let's start with the perception pipeline. And the very first thing in the perception pipeline is the other sensors. So the sensors are actually the access of the system to the physical world, right? Specifically, we use cameras and inertia measurement units, or IMUs, in ILLIXR. So IMUs include the accelerometer, which provides the linear acceleration along the XYZ axis, and also the gyroscopes that gives angular velocity also along the XYZ axis. So IMUs are usually very noisy and cannot give very reliable readings, but they are very fast and can run at very high frequencies, such as hundreds or even thousands of hertz. So we can obtain very fast estimates on what the user is doing with the IMU inputs. And to complement IMUs, there's also camera. Cameras can provide much more information about the user's surroundings because it actually shows you what it looks like, right? But the drawback of camera is it is slow and it can only run at tens of FPS. And there are also many different types of cameras, such as the normal color cameras, which with different field of view. There's also depth cameras that can provide depth information. So in ILLIXR, we have interface for a few different cameras. The one that we use most often is called that Mini, which is developed by a company called Stereo Labs. So it has nice sensors where you can obtain stereo images, which is a left eye image and right eye image in a time synchronous way. It can provide IMU readings up to 800 hertz, and it can also even provide depth information. So later we will show how different downstream components will take use of all this sensor information. But one drawback about that Mini is that its camera is a rolling shutter camera, which means each line of the image is not from the exact same point of time. So if there are many moving objects in the scene, and if you set the exposure time to be too long, then there will be many bad artifacts, and that will make it hard for tracking to do a good job. But we can still make it work, and we actually make it work pretty well inside ILLIXR after careful tuning and calibration. Another camera that ILLIXR supports is the Intel RealSense, and specifically on the D series. So this camera provides better depth information. It is also a global shutter camera, so there's no issue of the artifacts, but it has slower and also noisier IMU sensors. So we can see there is actually a trade-off when selecting different sensors, and it really depends on the needs of your downstream components. But what is more important here is that ILLIXR actually provides an interface for both these cameras, and there's a generic API defined for things like image formats and IMU reading formats, so that you can use that to create interface for other cameras that you want to integrate into ILLIXR. Okay, now we have this sensor information. We are going to use them to answer one important question, which is, where am I in the world? Right? And this concerns with a huge domain of tracking, which is widely used in things like in robotics and also autonomous vehicle. But specifically for the case of XR, it's really about tracking the user's head. So to understand where the user's head is, we need both the position and which is a 3-degree, 3-degree of freedom pose, 3-degree of freedom information on XYZ, and also the orientation of the user's head, which is also 3-degree freedom. So together we got a 6-degree of freedom pose, or a 6-DoF pose. So there are two common approaches of doing head tracking. The first one is the outside-in tracking, which means that we are utilizing some external devices, such as the base station shown here. In ILLIXR, we have support for that using the Valve Index Lighthouse system. So in this system, the base station is emitting infrared lights, and there are also sensors on the headset and the controllers that receive the infrared lights. So then based on the timing that when the sensors receive the lights, the system could calculate a very accurate position and orientation of the user's head at high frequency. However, the drawback of this approach, of the outside-in tracking approach, is that it is a restriction on the user's mobility, because the user have to move inside the range that the base station could cover. Another approach of head tracking that doesn't have this restriction of mobility is the inside-out tracking, which uses only the built-in sensors on the device, such as cameras and IMUs. So in Elixir, the inside-out head tracking pipeline starts with cameras and IMUs, and then there's a visual inertial odometry, or VIO, which takes inputs from the cameras and IMUs and generates the pose estimates by tracking the salient features across images and estimating how these features actually move across images. So there are tons of VIO algorithms and implementations out there using different feature representation, feature tracking methods, and pose estimators. So in Elixir specifically, we support OpenWinds and OpsLAM 3. VIO is good at accuracy, but the problem with it is slow because it's limited by the camera frequencies, and which can only run at 30 or 40 FPS, or like tens of FPS. This is really not enough to satisfy the pose query frequency of downstream components. So for example, the rendering is usually running at 90 Hz or even 120 and 144 frames per second, right? And also the user's CAD can actually move pretty fast. So you can imagine that the user's perspective and point of view have changed a lot in like 33 milliseconds if the camera can only runs at 30 FPS and the VIO is also running at 30 FPS. So to provide faster pose queries, to provide faster poses to satisfy the downstream components, we have another component in the head tracking pipeline, which is the IMU integrator. So IMU integrator runs at the same frequency of IMU, which can be up to hundreds of hertz, right? But due to the noisy nature of the IMUs, the pose estimates from the IMU integrator is not super accurate, and it can have bad drifts if you rely on it for extended time period. But it can usually work very well on the short time horizon, such as like 33 milliseconds between two VIO poses. And also the VIO usually has the functionality of estimating the noise model and biases of the IMU sensor. So use that information, we can actually cancel out or try canceling out the noises in the IMU sensor. So the IMU integrator can maintain a good accuracy for even longer time. And in Elixir, we provide two implementations of IMU integration. One is based on GTSAM, or the Georgia Tech Smooth Sand Mapping Framework, and another is based on the iterative Runge-Kutta four-step methods. Sometimes in the XR system, we would also need to estimate poses for a future time point so that we can start the processing earlier and make whatever deadline that we have. For example, if we know that we want to display some frame 10 milliseconds, we have to start the rendering process right now. Then we want to have a predicted pose of what the user's point of view and perspective for 10 milliseconds later, right? And in this case, we would need a pose predictor, which extrapolates the most recent pose to a future timestamp. So there are different models of doing the pose prediction, and one common case is the constant acceleration model, which is pretty convenient and also cheap. So the idea here is that we assume the user's acceleration will not change in short time span, like in the next 10 milliseconds. So we can take use of the user's most recent pose and also the user's acceleration, which we can obtain from the IMU readings to predict the user's pose in 10 milliseconds or some other shorter time in the future. And this is what we used in Elixir. There are also models based on constant velocity and some others. And again, Elixir provides a well-defined interface so that you can easily implement whatever models you want to use inside Elixir. And finally, combining the VIO, IMU integrator, and pose predictor, we are able to provide the downstream system with fast and accurate pose and even future future poses if that's in need. All right, then there comes the next component, which is called hand tracking. So just as head tracking is estimating the user's head pose, hand tracking is providing the poses of the user's hand and maybe finger joints. So by obtaining the user's hand and finger joint poses, we can enable hand interactions with virtual objects, so to boost the immersiveness of the experience. And it's very common to use neural networks to do this hand tracking process, where you input some RGB images and maybe some depth images and also your current pose to the network. And the network will output a bounding box, which covers the area of your hand and also gives you the finger joints locations as shown in the right figure. We recently added this new functionality of hand tracking inside Elixir by implementing two hand tracking plugins that interfaces with the Google's Media Pipe. We use two models from Google's Media Pipe. The first one is a palm detector model, which detects the your hand's presence, your palm's presence, and outputs a bounding box around your hand, and also a hand landmark model, which detects your individual joints and show the joints positions just as in the right figure. All right. Then the next component of the perception pipeline is scene reconstruction. So as in head tracking, we are answering the question of where am I in the world? The scene reconstruction component is really answering the question of what does the world around me look like? Right. And this is important, especially for MR and AR, where you can actually interact with the physical world. So one example is that if you're in an AR or an MR scenario, and you throw a ball to a wall, you really expect that the ball will bounce back from the wall rather than go directly through the wall, right? And this would require some understanding of the existence of the wall and then of the texture and some physics properties of the wall. And this is where we really need scene reconstruction. So as in VIO, there are tons of different algorithms and implementations on scene reconstruction. They really differ on their map representations and data structures. And in Elixir specifically, we have a standalone support for infinite time, where it uses the iterative closest points for the tracker and to track the features across things. And also it building the map using voxels and the data structure of hash table. And we will talk more about this in the later section. All right, then the last component in this perception pipeline is called eye tracking, which again, as the name implies, it estimates the pose of the eye, or more exactly, where the user is looking at. So by providing this information, eye tracking enables many optimizations, especially on graphics. And one foremost example would be forward rendering. So the idea of forward rendering is that it leverages the human visual perception system that we usually only focus on a small region of a big thing, and we require very high resolution for that small region, but relaxed requirement on resolution outside that region, right? So if we can get this information of where the user is focusing at from eye tracking, then the forwarded rendering will only render a small region around where the user is focusing at in very high resolution, but use lower resolutions for other areas outside that small region. This will give us extreme power savings and also boost the performance. Yeah, another example enabled by eye tracking is a varifocal display. So when we know where the user is looking at and the depths that they're actually looking at, we can actually change the display or, like moving the display closer to the user, further to the user to create better immersions than just a fixed optics. The classic method of doing, back to the forwarded rendering, the classical method of doing forwarded rendering is glint detection, which means you actually have an infrared projector and you project some light to the user's eyes. And then based on the glints or reflections that occur on the surface of the user's eyes, you estimate where the user is looking at, right? But these days, neural networks really are taking over in this field, as it does in many other fields. And in this case, the neural networks actually gave pretty good performance, even with a relatively small network size and relatively cheap computation. And in ILLIXR, we have the standalone support for RITNet, which segments a eye image, like in the figure, into iris, sclera, and pupils, and other areas. And then there is a post-processing pipeline, which based on this segmented image, finds the center of the pupil, and then it shoots a vector from the center of the pupil to the screen. And wherever that vector intersects with screen, that's the gaze location. And if you feed that information into the application, then it can do forwarded rendering, and it can do other things like the varifocal display. All right. So this concludes the perception pipeline, and a short summary would be perception pipeline utilizes sensor inputs to understand where the user is in the world, what the user surroundings look like, where the user is looking at, and where the user's hand is. So all this information will then be utilized by the next pipeline, which is the perception pipeline. So one thing that I want to say first is that if you remember the higher level overview diagram that we showed before, you would notice that this visual pipeline is actually different from the extra application itself. Well, the application is responsible for actually render the pixels and handle users' interactions with the virtual objects and handle some physical simulations. The visual pipeline is responsible for actually take the rendered images from the app and display them on the display from a correct perspective in a timely manner. And I think I would say the most important component in this visual pipeline is reprojection. So the motivation for reprojection is that between the time that a frame is rendered and the rendering is finishing, there's some time passed, and it's very likely that the user has already moved within this time span, right? So if you still directly present the rendered frame to the user, that will not match the user's current point of view and perspective. And so the experience will be not perfect. But instead of doing that, like directly presenting the user with the rendered frame, what we can do is called reprojection, which we takes the latest pose from the head tracking pipeline, that represents where the user's head is right now, and we transform the rendered frames to account for the user's current position and orientation. So this figure actually illustrates that idea. So if we have a rendered image that corresponds to the user's pose some time ago, and if we know that the user actually turned left during the rendering process, we could it's actually the same effect as we rotating the rendered frame to the right, right? And this could effectively cause the motion to photon latency that the user will perceive. Something that we can actually do better than that. So instead of projecting to whatever the user's current pose is, we can project that to a future pose. And that is because between the reprojection time and the actual display time, there's also some latency, right? Because you need some time to actually transmit the pixels from the GPU to your display, and also the displaying itself takes time. So to account for that latency and possible movements of the user during that time, we can actually predict the pose of what the user would be, what the user's head will be at the display time and reproject to that time. So this would further reduce the perceived motion to photon latency. Another important function of reprojection is when the application fails to submit a new frame, right? So ideally, if we set the rendering frequency to be maybe 120, we would expect the application to submit a new frame every 8 or so milliseconds. But sometimes it cannot make it because the sync complexity is changing, so the time that you need to render a frame also changes, right? So if this happens, like the application fails to submit a new frame, there are two options. One is we just do nothing and we show the user whatever we just showed them, like 8 milliseconds ago. And this is definitely not good because the user has already moved, but we show them the same image, and that will greatly break the immersion. Right. Another option that we have is we do reprojection, and we take whatever frame that's most recent from some time ago, and then we take the current pose of the user on a even better a predicted pose of the user, and we reproject that old frame to account for the motions of the user. So one common implementation of reprojection is called rotational reprojection or 3-DoF reprojection, which means we are only counting the rotational motions of the user. And this is also commonly known as time warp, and this is implemented in ILLIXR based on some implementation from Oculus from 2016. But as we all know, the user will not only do rotational movement. We can also do translational movement by walking around. So ILLIXR recently adds this functionality of 6-DoF reprojection or open warp to account for the translational movement of the user. And we will talk more about this in the later session as well. All right. So another thing that we need to take care of is it's the artifacts that introduced by modern XR optics. So usually nowadays, there will be a lens in the VR headset that sits in between of the actual display and also the user's eyes. So that lens could cause a lot of problems. For example, it can bend the light. So whatever that's actually straight on the display, after the bending will become curved. And another thing that's and another kind of distortion is a chromatic aberration, where the curved lens will split the RGB channels. So instead of seeing a single color, you would see a spectrum of the red, green, and blue. And this could be pretty disturbing to the users. So what we can do is we can apply the reverse distortion. So as shown in this figure, if we directly display a normal image after the lens distortion, we will get something distorted, right? So, but what we can do is we know this distortion exists, so we apply the reverse distortion by watch this frame a little bit, so that after the lens distortion, we will actually get a normal frame. And this reverse distortion can be based on on a per pixel base, which is sort of expensive, and it can be also based on a mesh, which is like an approximation of the per pixel correction, but much cheaper, and has been approved to have very similar quality. And another thing we need to know is since we have the RGB channels, we really need separate corrections for each of the color channels. And our implementation, again, is based on an Oculus implementation from 2016. It is a mesh-based one, so relatively cheap. And it is actually fused with the reprojection process. So if you look into the ILLIXR, you can really just see one set of shaders that does all of the reprojection and lens correction. Okay, so this summarizes the visual pipeline, which is basically the reprojection and distortion correction, so that user could see beautiful pixels that reflect their point of view and perspectives in a timely manner. All right, then that leaves us with the last pipeline, which is the audio pipeline. The audio pipeline really takes care of creating 3D or spatial audios that actually reflects, that actually simulates the effect of knowing where the sound is coming from. So to create a very good immersive experience. So the first thing to create this spatial audio is we have to encode the sound into a specific format, which is a higher order ambisonics, or HOA. So how the HOA represents the spatial audio is that it imagines the user is in the middle of a unit sphere, and there are many different virtual speakers attached on the sphere, and we simulate the sound where the sound is coming from by attaching them to those virtual speakers. And also, so depending on how like the number of virtual speakers actually varies depending on the orders of the HOA. So if you have a one order HOA, you probably only have one virtual speaker, and then if it's two order, you have four, and then if it's three order, you have 16. And you can see the more virtual speakers you have, the more fidelity you have, but also more computation cost that you have to pay. So there's a trade-off there. The good thing about HOA is widely adopted in many industry products such as the AR cores and Oculus. So once you encoded your sound into this HOA format, you can do all sorts of things with it. And in Elixir, we did this audio encoding. We implement this audio encoding using this Leap Spatial Audio, which is open source library, where we convert the monophonic sound, which is like a sound source that its orientation and position. And then we convert that into an HOA sound field. This also accounts for the distance of the sound source, so we can accurately simulate the delay and also the attenuation of the sound. Okay, then the next step is to once we have this sound field, the next step is to play this sound where the user is in this application, right? But what we need to know is that the user will not be fixed at a certain position during the application. Instead, they will move around, right? And we have to rotate or zoom in, zoom out the HOA sound field based on the user's latest pose, right? This is very important because if there's a mismatching between the audio cue and the visual cue, for example, if the user sees that the audio source is moving away from themselves or moving closer to themselves, but the sound effect is still the same, that just greatly breaks the immersion. Yeah, so another important step in this audio playback process is that even though we encode the sound field into many virtual speakers in this imagined sphere, eventually the user have to listen to them through some physical speakers, which can be your headphones or earphones, right? So we need another process of binauralization that maps the virtual sound field to the headphones and earphones. And the idea is to mimic the way that sound actually interacts with the user's head, ear, and nose, right? And this is done by something called head-related transfer function, or HRTFs, which can capture the impulse response of how the user's head, nose, ear actually changes the sound. Putting everything together, we have a audio playback pipeline inside Elixir, which is also implemented using the Leap Spatial Audio library. And it's sort of not realistic to have a HRTF for every person because we all have different head size, node size, and ear size. So what we do is we take an average HRTF from the MIT HRTF library, but again, you can replace that with whatever HRTF models that you want to use. And finally, we take use of the port audio library to actually provide the generated audio buffers to the system and make it to the speakers. Okay, so this concludes the audio pipeline. And in this figure, we shows all the components that Elixir supports today in the perception pipeline, visual pipeline, and audio pipeline. And you can see for each component, we sometimes have different implementations, of different algorithms in different language. But what's good about Elixir is we actually provide a generic API and interface so that you could add in or replace the current components with whatever implementation and algorithms you want to use. Okay, but one thing that I want to stress here is that Elixir is not simply a collection of components or just a benchmark for a certain algorithm. It is actually a system with a very complicated data flow. So as shown in this figure, we have so many components. They are running at very different frequencies. For example, the IMU can run at very high frequency of up to hundreds of hertz. But you can see here the same construction is actually running at a very low frequency because we don't expect the surrounding world to change very rapidly. And there are different kinds of dependencies among these components. So if we see here, the VIO is the VIO takes inputs from both the IMU and the camera, but the arrow that connects them are different, right? We have one solid arrow and we have a dotted arrow. So the solid arrow means VIO is actually synchronously dependent on the cameras, which means whenever we have a new camera image published, the VIO has to run. So it's synchronous to the camera. And there's also the dotted line from the IMU to the VIO, which means VIO is just, asynchronously dependent on the IMU. That means whenever VIO needs to run, it only needs to take whatever is the most recent IMU data. It doesn't need newer IMU data, or it doesn't have to run every time we have some new IMU data. And you can see these two kinds of dependencies are all around, between different components. And all these components form multiple interacting pipelines, either tightly coupled or very loosely coupled. And each pipeline presents different quality of experience metrics. Like we have the pose accuracy metrics for the head tracking pipeline. We have many graphics metrics, such as the ones that evaluate image qualities for the visual pipelines and so on. So it's really not enough to just improve the quality of a single component at a time. Instead, we have to take into consideration of the entire system. So Elixir provides a very friendly interface or platform to facilitate such full system research. Elixir maintains a modular and flexible architecture here. So all of the components can be modeled as plugins, and these plugins can be separately compiled and dynamically loaded. So this allows the users to easily swap out or add new components and test their implementations in an end-to-end fashion. At the same time, Elixir also provides an efficient and flexible communication interface where these components or plugins will just need to specify the event streams that they want to publish to or subscribe to. And then Elixir will handle all the data dependencies and data communication and evoking of functions. So together, we made an end-to-end system that balances both flexibility and efficiency. So in terms of applications, Elixir supports either writing your own application directly to Elixir, Or you can develop applications using game engines such as Unreal and Godot, as long as they are compatible with the OpenXR standards. Elixir enables characterization of the full XR system with very standard end-to-end quality metrics. This will include the motion to photon latency, which is the time between the user actually moves their head until the corresponding pixels are displayed. Right, this is very standard, like commonly used metrics in XR. Other things include like metrics for image quality, such as SSIM and flip, and also you can collect frame rates, missed frames, and time distributions of different components, and also power consumption of the entire system. In fact, with Elixir, we have published the first of its kind results on performance, power, and the quality of experience of the end-to-end XR system, and many implications can be learned from those results. So if you are interested, please check out our papers. Okay, so that concludes the overview of extended reality and also Elixir. Then we will take like a 5 minutes break, and after that we will give a hands-on demo of how you can actually set up Elixir and run Elixir.
Well, thanks everyone for joining us today. My name is Stephen. I'm one of the contributors of Elixir, and today I'll give a hands-on tutorial on how to set up Elixir on your own machine and how to get started with research using our platform. So I would first like to direct you to our websites, elixir.org, which has information about our consortium and news on development of Elixir. And our documentation is hosted on another site, elixir.github.io. And this is a very comprehensive documentation of all of the functionality of Elixir. And the API docs is also hosted on the same site under the API section, and you'll be able to reference them in your development. And we also link to our GitHub repo on our documentation site. And here, our development is very active. There are usually two different versions of Elixir that we would recommend you to get. The first one would be just a master branch. We try our very best to test our master commits, but due to the amount of development happening in Elixir and the rapid pace, we might not be able to cover every configuration in our master branch. And if you'd like more stability, or if you ran into issues, first, you can try out our release, which is comprehensively tested on our supported platforms. But also, if you run into any issues in general with Elixir, please feel free to head to the issue section to file a bug report. Or if you have any ideas on how to improve Elixir, you can also either raise it here as with an improvement tag, or join us on our Discord, where we can discuss how Elixir can suit your needs. And in the pull request section, we have a pull requests from different branches as well, and we welcome you to and encourage you to upstream your changes to Elixir, so it's available to more folks. And the process is usually you can fork Elixir on GitHub, and you'll be able to open a pull request. I also want to quickly mention that we have a CI infrastructure, and for the first time you open a pull request, we need someone on the Elixir team to approve the CI workflow being run, because it's a comprehensive graphics test suite. We're currently testing the graphics pipeline of Elixir as well, and there are security issues associated with running unverified pull request. So just open a pull request, then someone will quickly review your code and approve the CI workflow. And all of the development of Elixir happens in this repo. So if you're interested in keeping up to date with Elixir's development, the GitHub repo would be a great option to do that. So I'd like to get back to the documentation and talk a little bit about how to get started with Elixir. So our overview page provides some of the more generic information about the different functionalities and plugins, and we have a section about our publications as well with links to our paper, demo, and more resources. We also have demo videos here, and here's the citation as well, and licenses. So to get started with Elixir, let's go to the Get Started section, and our platform currently supports Ubuntu 22.04, 24.04, and Fedora 38, although Fedora is less frequently tested compared to Ubuntu. And the first step to get started with Elixir is cloning using Git. And here we just cloned a single branch, but if you're interested in using the release tag of Elixir, you also have the option to switch branches, switch to that commit hash, or just download the source code using GitHub's zip function. You can get the source code here as well. And the next step is to select which operating system you're on. And you can see here we have an interactive configurator that helps you find a configuration that suits your needs, and the options you select here affects the commands that the configurator generates. So here, let's stick with Ubuntu, and the next step is to pick out the plugins you want to run. So I'll dive into plugins a little bit more later, but they're basically a modular implementation of logic and functionality in Elixir. So for example, there are two ways to configure Elixir. The first one would be to select a pre-configured profile here. And these are just pre-configured YAML files based on a variety of use cases. They're tested by our team and they're ready to go. So if you're just getting started, this will be a great starting point. So here, I like to use the native OpenWarp VK profile as an example, and I'll dive into what this profile does a little bit later. So here, after we selected the profile, we can see that an array of plugins are automatically selected, and these would be the plugins included in this profile. And so this would be the first way to configure Elixir. And another way is by selecting the plugins directly. As you can see, we can do some check marks here, and the commands generated will be different as well. So this part would be more suited if you have a good understanding of Elixir's architecture, because the plugins have data flow dependencies that need to be satisfied in order for Elixir to run. And a really great resource if you want to understand the data flow is the graph here, where we map out the complete data flow for every plugin and service in Elixir. So if you're looking to pick out your own plugins instead of using a profile, that graph would be a great resource to have, and it's under plugin overview. So let's go ahead with native OpenWarp VK for now, and let's move forward with the configurator. So here we can see that it automatically generated a list of dependencies to install on Ubuntu, and these are actually dependent on which plugins you select. And the next step is to build Elixir, and here the command is also adapted to the profile we selected. And I'd like to make a quick note on CMake install prefix. So Elixir has recently moved to the CMake build system in our new release, and it's much more convenient than our old build system because it's tailored to the build process, and we have no custom Python scripts. So this should work on across all platforms that support CMake, and the commands are listed here. So the CMake install prefix is a CMake variable that defaults to user local. However, in our development, we usually set this to a custom location because when the machine is shared between multiple people, there may be conflicts when Elixir is all installed to user local. So it would be great to set this to a location in your own in other directories to avoid conflicts. So I actually like to set it up right now using the command provided to me here. So here I've already cloned Elixir. I've created a build directory, and the next step would be to copy this and change the install location. And here I'm just gonna set it to the install folder in the build directory. So as you can see, the CMake configuration here is complete, and we have a really nice summary of the enabled functionality and the configuration of the current state. And it would be nice to double check that all of the plugins you need are shown as enabled here. And we also have instructions on how to run Elixir. So a quick note, if you set a custom install directory, you would need to set a LD library path to this path as directed, because LD will look for libraries in user local, but not in the custom install directory. So we need to supply it to the program. And there's also CMake build type. If you're doing development, you should set it to debug or release with debug info. But if you're doing profiling, these two will be appropriate as well, because we want the maximum performance available. So the next step would be to build Elixir. And here, the build command is also provided. And you can change our argument J4 to however many threads you want CMake's underlying generator to, CMake's underlying build system, in this case, make, to run in parallel. So I have a 32 core machine. I'm just going to do J31. And because I've built Elixir before, the process here is fairly simple. And the last step, don't forget to install it using the CMake install command. So that's it. Elixir is set up on my machine. And there are two ways to select which plugins to use, and I want to quickly mention here. The first way is to use a profile like I did here, but we can also use the command line flag use plugin equals on to toggle plugins on and off. And for example, if we add some more plugins, these don't really make sense, but just for the sake of it, if we add more plugins, we can see the generated command changed. Instead of using a pre-configured profile, it would use these command line flags to enable the plugins. So let's go back, and if you're interested in building the documentation, you can also do that using this command. But this just builds a documentation that's exactly the same as this website, so you can also just use this website. Great. So we've installed it, and I'm now going to demonstrate how to run Elixir. So let's do LD library path because we use a custom install directory. Let's set that to what was instructed in the cmake configure command, and let's run Elixir. Perfect. So as you can see now, there are two windows in the native OpenWarp BK profile. The first one is the iBuffer window, and this would be what will be presented on the display. It's currently showing up as a window because we don't have a headset connected, but we have description on how to configure direct mode for headsets as well. So you'll be able to directly present the iBuffer on the headset with the right environmental variables. And the second window here I like to draw your attention to is the debug view. Oops. Okay. And here is a representation of a very, let me run that again, since okay, perfect. So this is a interactive window in a toy environment. So we made this Elixir room, and you can see the headset moving. Here, the onboard camera views are the stereo view of the camera on the headset. Here we're using the UROC dataset, but you're also able to connect a Z, RealSense, or whatever camera we support, and the camera feed would be displayed here. So on the bottom right, we have another panel that displays the pose and IMU data of the headset. And there are also some configuration options on the third person rendering of the environment. So that's Elixir's native profile. We call it native because the app that's running right now is called VK Demo, and it is a it is kind of a test application that's hosted inside Elixir. So we're not doing OpenXR, and this is completely within Elixir. So this will be helpful if you're doing development on the graphics pipeline and you just want a simple application to test with. So that's how you set up and run Elixir. You're also able to select a profile that works with OpenXR. So for example, if I select Monado OpenWarp VK, which stands for the Vulkan implementation of our Monado integration with OpenWarp, which we will talk about more, it is a 6-degree of freedom spatial reprojection algorithm we proposed in our recent paper. You'll be able to run with Monado using an OpenXR conformant app. So great. I'd like to talk a little bit more about the plugins and services of Elixir. So these are some concepts we have in Elixir plugin services. A plugin is usually a loop that's a class that runs on separate thread that schedules itself. So if you have any tasks that need to be run in a loop, a plugin would be our way of implementing it. And a service, on the other hand, is a modular component initialized by a plugin, but they provide callable functions to other plugins. So services are not directly triggered by Elixir's main loop or by any other mechanism except for directly being called. And a good example is post prediction, in which we use the latest IMU values to predict a post at some point into the future. And because there is not really a need to run this on its own, it's implemented as a service where plugins can call the different functions in post prediction and provide either the present time or time point in the future to get an estimated post. So that's an example of a service. So I'd like to take a 5-minute break here, and after the break, I'll dive in a little bit more into Elixir's code base, show you how to write your own plugins, introduce the concepts of topics, phone book, and switchboard. These are some of the core components in Elixir, and introduce the resources that can help you if you run into any issues during your development with Elixir. So let's take a 5-minute break here. Great. So hi everyone, let's get back to part 2 of the hands-on part of our tutorial. And in this part, I'll go over how you can quickly get started with your own plugin for Elixir. I'll introduce some core components in Elixir, such as switchboard and phone book. And then I'll talk a little bit about the resources you can use when doing development for Elixir. So the first page I'd like to point you to is our tutorial page for how to write a plugin. And we have very detailed instructions on how, step-by-step instructions on how you can create a CMake lists file to include your plugin in the build system. And we have different examples here based on what kind of dependencies you need. And here we actually start with a very basic plugin, and this is the structure. So thread loop is a helper class we provide to plugins that need to schedule themselves. So let's just quickly go to the API page of thread loop. So we have very detailed documentation here on the functions that a thread loop needs to implement. So there are the virtual functions here, and I'll give a quick introduction to what these functions do. So the first method, P1 iteration, is called for every invocation of the loop. And basically your application logic would reside in this function. And the P should skip function, which returns a skip option. And the options here are run, skip and spin, and skip and yield, and stop. So the 4 options here determines what thread loop does for the next iteration. So for example, if you return run, the next iteration will be immediately invoked. And if you return skip and spin, it will do a spin wait. And if you do skip and yield, it will call thread.yield to give up the time slice. So this determines how frequently your iterations run. Basically, if you want to time your iterations, this will be a good place to do. And the third function is pthread setup, and this is called at the initialization of the thread loop, and it would set up the you can put any setup logic in this function, and it will only be invoked once at the start of the thread. So the reason we have thread loop is because the constructor of each plugin cannot be blocking, meaning that you cannot have any loop running in the constructor. So what you would do is to extend from this class, and it will help you launch your own thread for the plugin. So I'd like to show you an example of how a plugin in Elixir utilizes a thread loop. And here we have the Z plugin. Excuse me. The Z plugin handles the camera input from the Z Mini, and it puts IMU and camera data onto the topics, which is something we'll cover later. So let's focus for now on the thread loop part of the Z plugin. So as we can see, the P should skip here determines how frequently the iterations are run, and here if the IMU timestamp is greater than the last IMU timestamp, we sleep for 2 milliseconds. So you can use sleep here to control the frequency. And here, the P1 iteration actually handles the logic of getting the IMU data from the Z and putting it into a switchboard topic, which we will cover next. So this is an example of how you would use a thread loop to schedule your logic in the plugin. So next, let's take a quick look at switchboard, and the main thing I want to talk about is topics. So let's go to the switchboard page of the documentation, and as you can see, we have a lot of functionality related to topics here. The main ones being a get topic, get writer, get reader, and get buffered reader and get network writer. So the writers and readers are all they all operate on a topic, and the topic is specified using the string here, the topic name. So let's look at an example of writing to a topic first. So let's stick with the Z plugin here, and let's first see how we can initialize a topic. So here, let's close the other file for now. So here, the Z plugin gets a writer for the IMU topic, and this writer allows you to put messages into the topic. So let's see where this is being used. Search for it. So here, line 1, 13. So after we got the acceleration data and the other data from the IMU from the Z camera, we allocate a new IMU type, which it is a struct we define that contains all of the data we need, and we allocate that and put it into the topic. So the put function on the writer just puts any data you specify into the topic. So that's how you would write to a topic. And let's now look at reading from the topic, and there are mainly two ways: a synchronous reading and asynchronous. So by synchronous, what I mean is the application logic is scheduled by the topic itself. So what do I mean by that? Let's look at an example of schedule. So to do synchronous reading, you would call the schedule function here, and an example would be our GT-SAM integrator. So let's open that up, and let's look at line 26. So here it schedules a callback on the IME topic, which the Z plugin has just written into, right? We just showed how you would write to the IME topic. So here we schedule a callback, and let's see what it does in the callback. After a callback has been scheduled on a topic, anytime a message is put into a topic, the callback is called, and the logic is specified here. Here we just place back the IMU data into a vector. So I want to quickly disambiguate synchronous reading with blocking, because the put function of the writer is not blocking. Whenever you schedule a callback using the schedule function. For each subscription, we will launch a new thread that calls the callback. So the put function in the writer doesn't need to wait for all of the callbacks. All of the callbacks all have their own threads. So any logic you have in the callback, you need to consider for concurrent access if you're also using a thread loop in your own plugin and the data is accessed there. So that's an example of synchronous writing. And now let's look at asynchronous writing. So these would be the get reader and get buffer reader function. So let's first look at the get reader function. And a good example would be time warp. The time warp plugin. Let's actually go to the time warp bk.cpp. So here we got a reader for the topic vsync estimate. So Qingjun covered a little bit of how reprojection works, and we need the vsync in the warping plugin, reprojection plugin, because we need a good estimate of when the next vsync is, and we want to warp the image to the pose we think the user is going to be at that point in time. So we would call the prediction function in pose predictor using this vsync estimate. And we get this by getting a reader on the topic. And let's see how we actually operate on the reader. So here we read from the reader using get a read-only nullable, meaning that if there's no message on the topic, it would just return null. Otherwise, it would return a read-only pointer of the last message on the topic. So a key point to note about the reader class is that it only grants you access to the latest message on the topic, just one. And that's all we need here in time warp, because we don't really care about the historical vsync times, although we might care about them for different purposes, but not here. Here, we just need to get the latest estimate and warp the image to that point in time. And that's how you would use a reader. Another option, if you want to have a queue structure on all of the messages in the topic, is the buffer reader. So let's see an example of how you would use the buffer reader. So this plugin is the offloading rendering plugin, and it is the client of the plugin. So just a quick recap of how offloading rendering works. The server sends compressed images, and the client needs to decode them, and then another reprojection plugin, either time warp or open warp, would do image-based rendering to reproject them to the correct pose. So the first step is to get the frames, right? So the frame reader here gets a buffered reader on the type compressed frames, which contains our encoded frames. And here we need to decode them. Let's see how you would actually use the buffered reader. So there's only one function that you would call in the buffered reader, and it is dequeue. Dequeue removes a message from the buffered reader in a FIFO order. So it would actually give us the earliest frame that was enqueued in the queue. And it would be blocking as well. So if there are currently no messages, the buffer reader would block until something is added. So the reason we use the buffer reader here is because due to how compression works, we need access to historical frames in order to decode the next. So everything needs to happen in sequence. And that's why we need to use the buffer reader here. And and as you can see, topics are a pub/sub kind of event stream that we have in Elixir. And I would now like to point you to the resources we have for developing Elixir. And the first one would be the API docs embedded in our documentation. And I've talked a little bit about how you can raise issues and open pull requests on our Git repo. We have a CI workflow to make sure everything works as intended. And to ask for help, I would highly encourage you to join our Discord, which we also linked. We linked on our GitHub page. So you can join our Discord here for any questions you might have. So that's all for the hands-on part of Elixir, and thank you again for joining us today.
Hi everyone. So next of the tutorial, we will deep dive into the research around distributed XOR and talk about what motivates and what research projects we have done under this topic, and what support we have in Elixir for you to do research in distributed XOR. All right. So as we said before, power consumption has become the first-order design constraint in XR devices. It directly affects the thermal comfort of the user and also the battery life of the device. It can also influence the device's weight and form factors because due to the battery size of the battery and also the cooling system support. As it also guides the compute capabilities, it partially determines the richness of the immersive experience that can be afforded with the device. So there are several approaches of reducing on-device power consumptions. The first one is distributed XR, or to offload heavy computations from the XR devices to some edge or cloud servers. The second one is through specialized hardware. And finally, there are some approximation opportunities to reduce computation requirement based on the end-to-end system and experience analysis. So today we will focus on the approach of distributed XOR. We will first talk about two papers from the team on offloading head tracking and rendering, which are the top compute and power consumers in our profiling results. And next, we will discuss other offloading opportunities and features in Elixir that are designed for distributed XR research. Okay, let's start it with offloading head tracking. So previous work has shown that VIO or head tracking is a top consumer of CPU cycles and thus makes it a great target for offloading. Another option for reduced VIO power is hardware acceleration. However, hardware acceleration brings in high engineering cost and is not scalable given the still influx algorithmic advancements. In contrast, remote offloading is hardware independent and saves the engineering cost, while also can easily adapt to the changing algorithms. Therefore, we choose this approach of remote offloading in this work. So there are two challenges for remote offloading compared to hardware acceleration. And the first one is, will the user experience be still acceptable given the introduced network latency? The secondly is, will there be net power savings given the extra power spent on network transmission and data compression and decompression? So to address these challenges in this work, we present Remote VIO, which is the first open source end-to-end XR system that offloads VIO. Remote VIO preserves satisfactory user experience under normal network conditions and leads to significant power savings. Meanwhile, results obtained from remote VIO question the common methodologies used in prior work for evaluating XR system performance. So to evaluate the effectiveness of an XR system with VIO offloaded, two critical aspects must be thoroughly examined. The first aspect is the end-to-end user experience. By end-to-end, we mean that the user can put on the headset and have a real immersive experience where the system supports all the components and computes from the sensor to the display. Unfortunately, previous work usually builds just a partial system with only the components relevant to tasks to be offloaded, and therefore cannot have an end-to-end user experience. And based on such partial systems, they collect component-specific metrics which have an undetermined relationship with the actual user experience. In contrast, our work built Remote VIO, the first open-source end-to-end system with VIO offloaded. With Remote VIO, we conducted a user study with 30 users and 246 trials under various network conditions to prove that Remote VIO can preserve satisfactory user experience under normal network conditions. Also, by cross-checking the user experience with component-wise quantitative metrics, we uncovered the limitations of these standard metrics in representing user experience. Another aspect is to ensure that offloading brings net power savings by accounting for not only the remote compute, but also the overhead introduced by network transmission and payload compression or decompression. So existing works usually infer power usage from observed CPU and GPU utilization without directly measuring them on real hardware. They also tend to overlook the overhead of data transmission and codecs. In contrast, we measured power consumption of Remote VIO on real hardware with a similar power envelope as mobile devices. Our results showed that Remote VIO saves on average 13% power consumption for the entire system and on average 30% for just the CPU plus the network. Okay, so now let's review some background which was also covered earlier today. So the head tracking pipeline has VIO, which is slow but accurate, and also the IMU integrator, which is fast but less accurate. Combining both, we have the chance to get poses that are both fast and accurate. And meanwhile, we have ILLIXR, which provides a highly modular architecture that allows easy extension. So, taking advantage of ILLIXR and our insights into the collaboration between VIO and IMU integrator, we built Remote VIO with a client-server architecture. We moved the intense VIO computation to the server by sending the compressed camera images and IMU data to the server and getting back VIO poses. Meanwhile, we keep the IMU integrator on the client to keep supplying poses to the downstream system. Exploiting ILLIXR's highly modular structure, we implemented new ILLIXR plugins to handle TCP transmission and reception, and also with H.264 encoding and decoding of the camera images. And finally, we also applied a low-pass filter on the client side to smooth out jitters caused by the accumulated errors in the IMU integrator. To evaluate the performance of Remote VIO, we developed two experimental setups. The first one is a production setup for the user study and also power measurements. So the client can either be running on a desktop or an NVIDIA Jetson AGS Xavier for power measurements, and we will thereafter refer to that as a Jetson. The server runs on an AWS EC2 instance. Client and server could communicate via Wi-Fi and 5G. And the users can see rendered content through a Valve Index headset with a Z-Mini camera attached to the front for live sensor inputs. We also use real XR applications developed with Unreal Game Engine to create a realistic immersive experience. We also set up a local system for some of the user study with fixed network latency and also a network latency sweep to stress test the system's capability. In this case, the client and server are both running on the same desktop and talk through localhost. We used Linux Traffic Control or TC to inject network latencies. To make the experiments repeatable, we used the commonly used UROC Wycon Room datasets and the 3 other self-recorded datasets, which are tailored to the XR scenario. Finally, for the metrics, we conducted a user study to fully understand the real user experience. We also collected the standard tracking accuracy metrics, such as the absolute trajectory error, or ATE, and relative pose errors, RPE, and examined their effectiveness in reflecting the user experience. Okay, let's talk about the setups of the user study. So we conducted an LRB-approved user study that involves 30 participants, among which 13 are females and 17 are males, and they are aged between 21 and 57, with varying experience with XR. We tested with 2 applications, as shown here. The left one is Zen Garden, which has a beautiful graphics, and the user could walk through it. And the right one is Flight Simulator, where the user can use controllers or keyboard to actually fly an airplane. We tested under 8 network conditions, and 2 of them are the live 5G and Wi-Fi when offloading to the AWS server, which is about 300 miles away from the testing site. Another 2 are with the 5G simulator and replaying 5G traces recorded in real life. And the final 4 are fixed round trip time, or RTT, which are set by the traffic control TC. So for each application, under each network condition, the users answered a questionnaire and compared the remote VIO experience with the baseline experience, where the baseline experience means the VIO is actually running locally without offloading. So before we dive into the results, let's first see a video demo of the user experiencing the applications in Garden, where VIO is offloaded to the AWS server via Wi-Fi. As we can see, the experience is quite smooth and pleasant. All right, so now let's take a look at the user study results. This figure presents the user's ratings of remote VIO compared to the baseline experience for 2 applications and 8 network conditions. So on the x-axis, the network conditions are ordered with increasing average network latencies. As we can see, remote VIO preserves satisfactory user experience under normal network conditions, such as in live Wi-Fi, live 5G, or the 2 5G traces, and even up to 100 milliseconds. However, for latencies beyond that range, for example, at 400 milliseconds and beyond, the user experience degrades significantly. Unfortunately, the standard tracking accuracy metrics do not capture the trend that we observed in the user study results. In the right figure, we reported the ATE errors for 12 dataset when network round trip time goes from 0 to 1 second. So as we can see, the error increases mostly slowly as the network latency goes up. Meanwhile, the range of ATE and the change of ATE with latency both vary for different datasets. While RPE also has similar trend as ATE, we can conclude that these standard metrics are not a reliable predictor of user experience. We also tried correlating these metrics with our user study results. And in this figure, we plotted the user's ratings with corresponding ATE and RPE. Apparently, there's no obvious correlation between the metrics and the user's perception, which suggests that we need better metrics that correlate with user experience. We also collected users' responses on what contributed to the degradation of their experience. As we can see, jitter and lag are the most perceptible artifacts in our study. So the implications here are, first, future works can seek to improve these 2 artifacts to improve the user experience. And also, we need some quantitative metrics to actually reflect the appearance of these metrics so that we can accelerate the system design and the evaluation process without having to do a user study for every system improvement. Okay, finally, let's take a look at the power measurement. Since we are presenting an offloaded system, it is critical to assess the power consumption of wireless transmission and ensure that the benefits of offloading is not outweighed by the network overhead. So to do that, we tethered the Jetson to a mobile phone and read the phone's power rails on the different network modes. By different network modes, I mean we have airplane mode, where the network is actually disabled. There's also the standby mode, where the network is enabled, but there's no traffic activity going on. There's also the activation mode, where we enable the network and we are transmitting some small traffics to simulate a normally seen scenarios in XR. And finally, there's the offloading mode, which represents the real traffic going on when remote VIO is running and we are offloading to the AWS server. So as most XR devices nowadays require access to the internet to use their features, we safely assume that the radio will be kept on and transmitting data even without VIO offloading. Therefore, the wireless power consumption for an XR device without VIO offloading will be similar to the power in activation mode. We add that to the power consumption of the baseline system to get a full system power consumption in the next slide. We also conducted power measurements of the baseline system and the remote VIO system on the Jetson with 9 datasets and 2 applications. The two applications are with different rendering complexity, so different compute demand and power consumption. So as we can see in this figure, remote VIO achieves on average power savings of about 2 watts, which translates to like on average 30% savings for the full system. And if we consider only the CPU part and network, the savings are on average 30%. So this carries great value for power-constrained XR devices in terms of extending the battery life and reduce heat emission. So in conclusion, we present Remote VIO, which is a first open source end-to-end XR system with VIO offloaded. Through our user study, we proved that Remote VIO preserves satisfactory user experience under normal network conditions, such as live Wi-Fi and 5G. Through a power measurement on mobile class platforms and account for the wireless transmission, we show that remote VIO saves on average 30% of power for the full system and 30% for the CPU plus network. We also identified that standard tracking accuracy metrics do not correlate well with user experience, which conveys 2 important messages. Firstly, it is important to conduct end-to-end XR research and evaluate user experience to guarantee the system usability. As we understand the great effort in building an end-to-end system, we hope our open source systems such as ILLIXR and Remote VIO can help the community to adopt the end-to-end approach. Still, conducting user studies on end-to-end system is time-consuming. Therefore, we need better methodologies, which involves metrics, datasets, benchmarks that are tailored to XR and can reflect user experience. Such a methodology will largely accelerate the design, evaluation, and refinement cycle for end-to-end XR system research. Okay, now I will hand over to Jeffrey to talk about our work on offloading rendering. Thank you.
Cool. So as Chinjun mentioned earlier, the XR graphics pipeline is another huge power consumer, but visual quality plays a huge factor in a user's experience. And traditionally, the device is responsible for application rendering. So it will get some poses from the XR runtime and will try to render at some target frequency. And there is a notion of reprojection where we want to compensate for maybe tiny bits of latency between the render and display time, or if you miss a frame every so often. But in our system, XRGo, we move application rendering entirely to the server. And by moving rendering to a server, the graphics workload on the device becomes a lot lighter. It only needs to decode the latest decoded frame and reproject the latest decoded frame according to the user's current pose. And as discussed earlier, this is effectively asynchronous reprojection, with the source now being a video decoder rather than the usual renderer. And the main challenge now is to design an algorithm to efficiently reproject your frames to compensate for the network latency induced by offloading, while also being efficient enough to run in real power at in real time. So traditionally, XR algorithms use a reproduction algorithm known as time warp, which performs rotation-only reproduction to mitigate minor latency issues. And the issue is that since time warp is rotation only, it fails to properly handle the parallax effect. And when the user rotates outside the original frame, there's a visible black border. Both these issues become increasingly noticeable at higher latencies. So as we mentioned earlier, we designed OpenWarp, which is our lightweight mesh-based 6-degree of freedom asynchronous reproduction algorithm that compensates for both rotational and translational motion. How it works is by generating grid of vertices, which are then mapped to render depth images and then transformed via the inverse projection and view matrices to construct something called a reproduction mesh. And what's nice is that the render depth comes as part of OpenXR. So any applications that provide render depth are immediately supported by OpenWarp. You can think of this reproduction mesh as a sort of approximation of the rendered scene, which allows us to re-render the mesh at new poses. And this accounts for any translational movements as well. And although it's sort of a rough approximation, it does pretty well for the common case. And so naively, the reproduction mesh is only an approximation. So without any adjustments, you might run into some strange artifacts like stretching, where the background and foreground colors are stretched very obviously. So to mitigate this, we first check the neighboring depths to see if a vertex is at the boundary of a foreground and background object. And if we identify such a vertex, we shift it to the foreground to minimize this really intense color interpolation. This helps a lot, and although it has its own artifacts, we find that in general, it's a lot better than without this adjustment, and usually it's not as noticeable. So something else that's nice about OpenWarp is that it sort of decouples the server rendered field of view and the client's desired field of view. So what that means is the server can use a projection matrix with a higher field of view that will provide more surrounding information for the client. So when the client then re-renders at its desired field of view, there's potentially more information to work with. So in this specific diagram, we can see that the server is rendering some amount of information and the client only needs some amount. What's nice about this is for higher latencies, the client can still move left or right, and it will still have that information available to work with, and it won't encounter that black border problem that time warp sometimes has to deal with. So to evaluate how all this works together, we chose a client device to be the Jetson Orin that sort of emulates mobile specs and also supports running Linux and ILLIXR. And we attached this to the Valve Index as our choice of display headset. And our server was just a workstation with an RTX 4090. And for our encoding parameters, we chose 190 Mbps at 90 FPS. And here's just a quick demo of how it runs. So in this video, I'm tethered to the Jetson Orin, which is receiving frames from our workstation. And you can see it's pretty responsive with our reproduction algorithm. And yeah, continue. So for our scenes, we tested 2 scenes. The first is a popular graphic scene called Amazon Bistro, which is more outdoors. It's really shaded mostly with direct lighting, and overall the graphics level is just sort of moderate. And we also found a spaceship scene from the Godot marketplace, which is semi-closed, semi-open. It's shaded with more indirect lighting, so the graphics requirements are a little more higher end. Our entire study evaluated 29 users with varying experience in XR, and they were asked to compare an unrealistic baseline, which was tethered to a powerful desktop machine, against a bunch of different offloaded permutations with different network conditions and different warping algorithms. So we used 4 network conditions, which consisted of live Wi-Fi, a collected 5G trace, and then we also simulated a constant 20 millisecond and 50 millisecond latency using TC, as Shinjin mentioned before. And for each network condition, time warp and open warp were also chosen. And for each of these network conditions were shown in random order. And in between these network conditions, we would also randomly select time warp and open warp. And we would also randomly put in local rendering on the Jetson between these permutations. And users were, of course, allowed to refresh the baseline whenever they wanted to, because that's what they were asked to compare against. So we use the same rating system as offload rendering did, offload VIO did, and users were asked to rate their experience with the offloaded configuration against the idealized baseline, which was again tethered to the high NPC, where indistinguishable experiences were given a score of 4, while otherwise, depending on the severity of the degradation, the score decreased from 3 to 1, with 3 being slightly worse or almost the same, 2 was worse but acceptable, and 1 was much worse and unacceptable. So firstly, when we aggregated across all 232 trials of offloading with OpenWarp against all 232 trials of offloading with time warp, we found that OpenWarp is on average rated higher than time warp with statistical significance, with OpenWarp effectively getting a 2.9, so around slightly worse or almost the same. Now, furthermore, when we compared the simulated latencies against each other, as well as the live networks against each other, we found that in both comparisons, higher network latency contributes to a worse experience, which is what we would expect. But when we also examine the ratings for the live networks against the simulated networks with constant latency, we also found that the live networks also contribute to a worse experience. And what's important to note here is that the live networks had a lower average latency than the simulated networks, which sort of indicates that the variability itself is the factor that's contributing to this degradation in experience. And now just to show the results separated by scene and network condition, we still see that OpenWarp consistently maintains an advantage over time warp across all the scenarios. And I would also emphasize that pretty much every user, except for one user on one particular scene, rated the experience as always unacceptable when rendering locally. And that's because the Jetson cannot run these applications at the target 90 FPS, and it was only running at like 10 to 20 FPS at best. So as Shinji mentioned, it's really important to also understand how our algorithms affect our power, because although we found that offloading can help in terms of quality, we also want to make sure that it's helping us save power. And thankfully, our results show that this is indeed the case. So for the 30-watt TDP configuration on the Jetson, we found that offloading only consumes around 14% less power than rendering locally, where we would again note that local rendering was completely unacceptable because it couldn't read the target frame rate. So even when we tested on the 60-watt profile though for offload rendering, local rendering could still not hit the target frame rate. So in other words, you could spend almost over 3 times as much power on local rendering and still not achieve the same quality as offloaded rendering. And furthermore, something else that is important to emphasize is that OpenWarp uses almost exactly the same amount of power as time warp within 2%. So because OpenWarp always outperforms time warp in our scenarios, we find that OpenWarp is a really good choice of asynchronous reprojection when you're offloading. So to conclude, we introduced XRGo, which is an application transparent and OpenXR compliant XR rendering offload runtime built on ILLIXR with client-side asynchronous reprojection. And OpenWarp was our implementation of a lightweight mesh-based 6-degree freedom asynchronous reprojection algorithm. And using XRGo, we conducted a user study to show that OpenWarp consistently outperforms time warp, the industry practice 3-degree of freedom reprojection algorithm across a range of different network conditions. And we importantly found that experience also degrades not only with higher latency, but also due to network variability as well. And we also profiled the power consumption for local rendering and compared it with offload with time warp and OpenWarp. And we found that offloading could not only produce better results with 14% lower power, but because OpenWarp is within 2% of time warp's power consumption, it's a very good candidate for asynchronous reprojection while offloading. And overall, our results highlight the importance of using an end-to-end system to evaluate both user studies, power evaluations, and more. And again, we hope that these new features on ILLIXR can help support future research opportunities in the XR graphics pipeline, including video compression, reprojection, and more. Next, we'll talk about our general vision for offloading.
So we've talked about offloading VIO and rendering in detail. And we are currently also working on more offloading with scene reconstruction and scene understanding. But all of these offloading works require infrastructure in the runtime. And here I will introduce some architectural goals in our design to support future research in distributed XR. We are building a modular network interface inside Elixir's runtime for a flexible and coordinated distribution of the application and other computations. Uh, the network interface will support multiple network backends and deliver packets with fine-grained configuration. And based on the energy budget, network conditions, task deadlines, and user configurations, the runtime will make informed decisions on what to offload, where to offload, and provide guidance to the networking stack for more efficient network resource usage. So now I'd like to dive into the code base a little bit more to show how you can leverage Elixir's networking infrastructure. So we've talked a little bit about Elixir's topics, which is a pub/sub event stream that allows modular plugins to pass around data in an efficient way. And for networked applications, we created infrastructure for you to leverage this topics framework to pass around your data among multiple devices, which is coming in the future, but for now, pass around data between clients and servers using Elixir. So let's take a look at how this works. First, I'd like to show you the API interface for getting a network writer. So in Switchboard, we have a function called getNetworkWriter, which takes a string that's the name of the topic and a struct that are hints for the networking stack on how to schedule, packetize the data. So the network writer handles serialization for you automatically. So you just have to define your data structure, and then serialization will be handled by the runtime. So let's take a look at what kind of hints you can give to the networking backends on how to deliver your packet. We have priority, whether to retransmit the packet if it is lost, whether we want to allow out of order delivery, and what kind of packetization we want to use, and what kind of latency we want to make sure the packet is delivered by. So with these kind of hints, our network backends will be able to make more informed decisions on packetization, scheduling, and transmission, which are all transparent to the producers and consumers of the data. So if you're just writing a plugin in Elixir, this function is all you need to call, and you would use a network writer just as you would a regular writer. So it is all transparent to the plugins. So I would like to quickly show an example of using the network writer in the offloading rendering client. So here we need as Jeffrey mentioned before, we need to send the server the pose at which we rendered from the pose we need to send to the server from the client the pose the current pose in order for the server to render. And how we would do that is we would create a network writer, and the post writer we would just use as a regular writer, and everything will be handled automatically by the runtime, and the server will be read the post from this topic with no additional setup. And now we've introduced a little bit about how you can leverage Elixir's existing topics to pass data, transmit data on the network. Now I want to show you the interface of how you would create network backends, and this enables a lot of networking research and co-design between the systems and networking stack. So I would like to show you an example backend we have, the TCP network backend. This backend is a rather straightforward implementation that uses kernel TCP. And we currently don't make use of the hints, but we have networking backends in development that use more advanced transport protocols that could take advantage of the hints provided by the application and the plugins. So the API the interface we have here, I want to show you the structure of the class. It extends both plugin and network backend. So network backend is a interface for handling the serialized data from the runtime and transmit them over the network. So to create a network backend, we need to implement three functions. Topic create, that is whenever a network writer is being created and the topic doesn't exist. Is topic network is returns a Boolean on whether a topic is networked, and topic send means that we need to send a message on the topic specified here. So let's see how these are implemented in the TCP network backend. So the important part here, I would like to draw your attention to line number 129, topic send. Here we would just receive a string, which is just a byte array of the serialized message, and we would just send them over TCP using a very simple packetization scheme here. This is how we receive a message from the runtime and deliver it to our Elixir runtime on the other end, whether it's a server or it's a peer in a multi-client scenario. It's all doable within this network backend interface. And the next function I'd like to show you would be on line 166. So here, the topic received, it isn't part of the interface, but it is what we created ourselves. We have a little bit of control logic, but this method is just called when we receive a message from the TCP socket, and we call this ourselves. So here, what we would do is we would get the topic from switchboard, and we call the deserialize and put function, passing in the message and the hints, the net topic configurations that we previously recorded. And the message here, as you can see, is also a byte array, and the switchboard will deserialize the message first and put it into the corresponding topic. So with this interface, we can have a lot of possibilities on how we want to interop with the networking stack, and also the topology of the network can be defined by you as well, that to suit your needs in your own research. So this is a very rich playground for both the networking stack and system stack. So that concludes our deep dive into the code for the Elixir networking infrastructure.
Hi, this is Vignesh. Until now, we've seen distributed XR as one of the approaches of reducing on-device power consumption. What we'll do now is we'll present more examples of how Elixir or its components have been used for research for other approaches, namely specialized hardware acceleration and experience-driven approximation. I will briefly talk about the hardware acceleration work from our group that was done in collaboration with the ESP group from Columbia and published last year at PACT. So as we've learned until now, XR workloads have multiple components, like visual inertial odometry, scene reconstruction, and audio pipeline. And all of these can be candidates for hardware acceleration. Further, each of these components is further comprised of several fine-grained tasks like FFT or GEM. And if we wish to accelerate one of these components, say audio playback, the important question is, at what granularity do you want to accelerate it? Do you want to accelerate it with a specialized monolithic accelerator that fuses all of the computations of audio playback like FFT, FIR, IFFT, and all of the miscellaneous operations into one monolithic accelerator? Or do you want to decompose the monolithic accelerator that fuses the computations that disaggregates the computations for the fine-grained primitives like FFT, FIR, and IFFT so that they can be composed together on demand while running all of the other operations on the CPU? Each of these strategies comes with its own pros and cons. So a monolithic accelerator can have disadvantages like a potentially higher design cost because of its level of specialization. You can have lower accelerator utilization because you're unable to reuse its internal computations for other components. You'll have potentially increased area because of the complexity and as a result, higher leakage power. Also, these accelerators would not be extensible because they're less amenable to be reused for newer algorithms, and we know that algorithms are in flux in an emerging area like extended reality. On the other hand, disaggregated accelerators can suffer from performance degradation from what we call acceleration taxes. So what are these acceleration taxes that I talked about? Consider a heterogeneous system with a CPU and an accelerator, and both are integrated in shared memory. In our work, we study two taxes. So control tax is the cost paid by the application to invoke an accelerator and to ascertain that it's done or completed. And similarly, data tax is the cost paid by an application to move data to the accelerator and back from the accelerator. It's very important to note here that while we illustrate this data movement abstractly via shared memory, this could be implemented in different ways. For example, it can be via DRAM, or it can be between caches that are integrated with a traditional coherence protocol over a network on chip. A monolithic accelerator only pays this cost once, but a disaggregated system where you have multiple accelerators pays this cost multiple times. For example, the CPU needs to invoke multiple accelerators and ascertain their completion. Similarly, a disaggregated system also incurs data movement between the accelerators that again is implemented through DRAM or between caches over an interconnect. Since the monolithic accelerator only paid this acceleration tax once, it outperforms the disaggregated system for audio playback. What we desire is an ideal architecture that not only closes this performance gap between a monolithic and a disaggregated accelerator system, but can also improve the performance of both systems. We can achieve such an architecture by taming the acceleration taxes in a more decentralized fashion. So how do we achieve that? I introduce our work Mozart, which is a novel SoC architecture that leverages an optimized shared memory interface to integrate accelerators. More specifically, Mozart tames the control tax by introducing an accelerator synchronization interface with each accelerator. And what that allows is for the accelerators to be invoked through shared memory synchronization, even by each other, completely bypassing the CPU. Further, Mozart tames the data tax by using an optimized spandex FCS coherence protocol that facilitates optimized data movement between producers and consumers, all within a shared memory system that doesn't incur the overheads of a traditional coherence protocol, and it sort of emulates point-to-point data transfers. Finally, as a result, Mozart enables efficient chaining and pipelining of disaggregated accelerators entirely through software and requiring no additional hardware changes. And in this process, we also promote accelerators to be first-class citizens and not just devices in the system. In summary, Mozart shows that we can tame acceleration taxes by leveraging shared memory as a general interface. Specifically here, ASI tames the control taxes and Spandex tames the data taxes. By taming the acceleration taxes, we showed in our paper that Mozart can efficiently compose disaggregated accelerators, and shows that we can close this performance gap between disaggregated and a monolithic system. Lastly, we implement Mozart entirely in RTL and validate all of its benefits with complex real-world applications like audio pipeline, and all running on an FPGA. There's a link here of an artifact that we've evaluated with all 3 badges, and all of our designs and software are open source. Please see our paper for more details. Now I'll invite Rahul to talk about his research on experience-driven approximation for foveated rendering.
Right. So now I'll be talking about experience-driven approximation and specifically gaze-tracked foveated rendering. So as we have established that rendering is expensive, foveated rendering is one of the techniques that have been proposed to reduce this rendering cost. And the idea is you track where the user is looking and render that small region, the small fovea region, with high resolution, while the rest of the regions are rendered in a lower resolution. And this saves a lot of energy for rendering. Even though foveated rendering saves rendering energy, it requires gaze tracking, which is usually implemented through a DNN, and that adds additional energy of its own. And additionally, we have to consider strict motion to photon latency, which means the time when the user's gaze moves to the time where it's reflected in the rendered frame. A simplified version of this is fixed foveated rendering, where we assume that the user is always going to look in the center of the screen. So we remove the gaze tracking overheads. But now, because of this assumption, we need to have a larger fovea, and which means a higher rendering energy. This also means that as soon as the user looks on the sides of the screen, the rendering quality is compromised. So in a nutshell, the trade-off looks like this. For tracked foveation, we have higher energy because of the gaze tracking overheads, but the quality is better. For fixed foveation, the energy is low, but the quality is compromised. Ideally, we want best of the both worlds. So we approach this by approximating the gaze tracker. We use structured pruning and input downsampling for this. And this reduces the energy cost by 20x and latency by 9x. But the approximation causes gaze error, which in turn causes an overall quality loss. Now, to mitigate this quality loss, we keep the fovea size small, but we have a larger region of intermediate resolution before we drop to the ultra low resolution. So in principle, the idea is you degrade the resolution slowly outside the fovea with multiple layers of intermediate resolution or larger intermediate resolution. This has little effect on total energy, but it significantly improves the user experience. And for the first time through our co-design, we have tracked foveated rendering, including the gaze tracker, and that is more energy efficient than fixed foveated rendering and has better quality as well. Through our experience and through our experiments, we also realized that the metrics don't always match the user experience. And this is an ongoing area of research in experience-driven approximation. Next, I'll hand over to Boyan, who will talk about energy-efficient scene reconstruction.
All right, thanks, Rahul. So far, we've seen efforts in hardware acceleration and quality-reserved approximation. Now let's take a step back to rethink the trade-offs among the 3 key aspects: algorithm accuracy, execution latency, and energy efficiency. On a resource-constrained systems like mobile XR, we must make trade-offs to prioritize one factor over another. And with the fact that the usability of mobile XR devices is limited by battery capacity, here we have a particular focus on energy efficiency. The key to making these trade-offs is understanding design constraints and we will show shortly that these constraints are often overly strict and can vary depending on the downstream use case, which reveals a wide range of optimization opportunities that are often overlooked. In a complex system like XR, the optimal design decisions for a component depends on its downstream consumers. Here we show the dependency graph of a typical XR system from sensor inputs to machine perception modules, all the way down to rendering frames displayed to users. We will use 3D scene reconstruction as an example algorithm. And to simplify the visualization, we had all components and the data flows except those directly related to the reconstruction. And in this case, the reconstruction results are consumed by applications before being rendered to users, and the accuracy and the latency can vary widely across different applications. To better understand what I'm saying, here I have a video clip showing how scene reconstruction translates the physical world into virtual space, using camera inputs and their estimated poses. This input incrementally builds a globally consistent 3D model, which forms the foundation for advanced XR features. For instance, scene understanding, achieved through 3D object detection and instance segmentation, identifies objects for editing or interaction, while realistic spatial audio simulates sound reflections in the virtual space to create an immersive acoustic experience. These use cases have divergent expectations for accuracy and latency. Intuitively, scene understanding requires high reconstruction accuracy for object virtual physical interactions, but has very latency constraints depending on whether it operates on data comes from live streaming or offline scanning. In contrast, spatial audio can tolerate long latency and more accuracy loss in the reconstructed 3D model, as humans are less sensitive to sound, especially when they are calculated through reflections. To understand how the design constraints impact optimal design decisions, we conduct a case study on 3 energy-aware optimizations, each with configurable parameters that enable different trade-offs between accuracy, latency, and energy. For instance, increasing processor frequency trades energy efficiency for latency, while an aggressive input sampling compromises accuracy but reduces energy usage for completing the task. Their combinations form a set of designs that span a broad trade-off space and can satisfy diverse design constraints. We measure latency, accuracy, and energy usage of these designs on a mobile-level SoC named NVIDIA Jetson AGX Xavier. While we study 3 specific optimizations, the fundamental trade-offs they enable are broadly found across different optimizations. At a very high level, the trade-off space allows up to a 60x energy reduction, a 4x slowdown to 2x speed up in latency, and negligible to minor accuracy loss. Among all the design candidates, only a small subset form a Pareto optimal curve that outperform other designs in terms of energy savings, latency reductions, or accuracy losses. As downstream data consumers have varying accuracy and latency requirements, optimal designs are distributed along the Pareto optimal curve. Without exploiting this disparity, a suboptimal choice could lead to up to a 4x energy difference. Such cross-component analysis is critical for making design decisions that go beyond focusing on individual components, but is often challenging without a complete end-to-end system. ILLIXR serves this purpose by enabling plug-and-play customization to components through a simple and clear interface, and allows for both metrics and user-involved feedback, which we wish can further facilitate system research in the community. Next, I will hand it over to Yihan for other works with ILLIXR and our ongoing plans.
Thanks, Boyan. Next, I want to talk about research using ILLIXR by people outside our team. ILLIXR has been widely adopted in both academia and industry for research across multiple fields, including graphics, systems, architecture, networking, and security. Their works have been published in top conferences and journals, including IISWC, ASPLOS, TECS, RTSS, and Hot Mobile. One of the most exciting things about ILLIXR's impact is that many of these projects were done entirely without our team's involvement. This shows how easy it is for researchers to integrate ILLIXR into their own work on their own. So if you are working on XR research and need a flexible open source testbed, ILLIXR is ready to support you. Next, I will talk about our ongoing work and how you can contribute to ILLIXR. First, I will talk about the key directions we are focusing on for the next phase of development. ILLIXR aims to support the full spectrum of XR, making it a comprehensive testbed for all XR systems. Right now, we are working on adding support for mixed reality, which works like a video pass-through in commercial devices such as Quest and Vision Pro. While ILLIXR already provides many of the core components needed for augmented reality, future work will focus on better support for AR research, especially for applications with strict latency requirements. To better mimic real XR devices, we are also enhancing ILLIXR with several key real-time functionalities, providing open source alternatives to features found in proprietary XR toolkits like ARKit. Among these activities, ILLIXR extended its support for real-time scene reconstruction and provisioning. Scene reconstruction builds a real-time representation of the environment, and scene provisioning ensures that this data is available in structured formats such as meshes or point cloud. These formats are used in spatial computing tasks like rendering, physical simulation, and object interaction. This approach is similar to ARKit's scene reconstruction provider, which supplies structured scene data for applications. Work is also underway to add scene understanding to ILLIXR, where the XR devices can understand and classify real-world objects and surfaces. Comparable to ARKit's mesh with classification, this functionality provides an approximate shape of the physical environment along with the object classification, improving spatial awareness for AR applications. Lastly, we plan to introduce support for scene editing, where we plan to introduce tools for modifying virtual and augmented environment in real time. For example, changing the color or the rotation of the seat. This functionality enables interactive content creation and real-time collaboration. Beyond supporting core XR functionalities, we are also adding 3D Gaussian-based neural rendering to ILLIXR. Neural rendering, particularly 3D Gaussian splatting, offers high-quality rendering and can synthesize the view even where input view is missing. It has gained significant attention in computer vision, graphics, and even architecture communities. By integrating 3D Gaussian-based neural rendering into ILLIXR, we aim to make it a more versatile testbed and encourage more researchers to use ILLIXR for their work in this growing field. Furthermore, we are also extending ILLIXR to support Android, as many XR devices, especially AR glasses, run on Android-based systems. We are also adding real-world XR applications to ILLIXR to serve as benchmarks for evaluating system performance and supporting research on practical XR use cases. Two key areas we are focusing on are collaborative medical XR and holographic telepresence. First, collaborative medical XR is becoming increasingly important in healthcare, from remote medical training to collaborative surgery planning and XR-assisted diagnostics. By integrating medical XR application into ILLIXR, we are providing a flexible testbed where researchers can design and prototype systems that meet specific requirements, such as low latency, high precision, and multi-user synchronization. Another area we are looking at is holographic telepresence, which allows users to interact through realistic 3D reconstructed avatars for remote communication and collaboration. By incorporating this into ILLIXR, we enable researchers to experiment with real-time rendering, networking, and multi-user interaction, helping advance telepresence technology for more immersive experience. Lastly, we plan to release XR datasets used in our research. This includes the remote VIO XR dataset to support future research and development in this field. Next, let's discuss how you can contribute to the project. Whether you have a specific idea in mind or just want to get involved, there are multiple ways to participate. For example, you can always improve existing components. Let's be honest, no matter how much we write the cleanest, most optimized code, there's always room for improvement. If you see ways to enhance existing components, whether it's reducing latency, porting into new devices, or adding support for more network backends, just go ahead and do it. Your contributions can make a real impact. Every improvement helps push Elixir forward and benefits the entire XR research community. Furthermore, you can also add new XR modules to Elixir. This could be a new component for a different type of neural-based string reconstruction algorithm, or a brand new hand tracking system. Beyond just adding these components, this also allows you to evaluate how different implementations of the same functionality impact the full end-to-end system, also helping to advance XR research. Hey, if you're feeling more ambitious, you can take a step further by developing a full XR systems. This means integrating multiple components and extending beyond the existing profiles in Elixir. If you remember earlier, that a system is referred to as a profile. Unlike adding a single module, this requires coordinating multiple functionalities to create a more feature-rich and complete XR experience. Once you made a contribution, the next step is to submit a PR request. Please read the following contributing guideline page. It has all the informations and all the necessary steps you need to get your work reviewed and merged into the Elixir project. Hey, if you're thinking, this all sounds great, but I'm not sure I can jump in just yet, no worries. There are plenty of ways to get involved and ease into contributing to Elixir. A great way is by start checking our beginning-friendly tasks. Just scan the QR code on the right to access a starter task that walks you through setting up Elixir on your own machine and experimenting with it. This helps you get comfortable with the system before diving into development. Once you've set up Elixir and explored a little, you might be looking for more ways to contribute. Our GitHub repository has a list of open PR issues with tasks of very difficulty levels. Whether you are new to XR development or experienced researcher, you can always find something that matches your skill set. And if you ever get stuck, don't worry. The best way to get guidance is by engaging with other contributors. Join our Discord server via the QR code on the right and ask questions, discuss ideas, and connect with developers and researchers also working on Elixir. That wraps up our presentation. Now we'd love to hear from you. Feel free to ask any questions.